Right, hello A-level students. So this is an S2 paper from January 2010. Right, so question 1. A pilot records the takeoff distance for his light aircraft on runways at various altitudes. The data are shown in the table below, where A meters is the altitude and T meters is the takeoff distance. Also shown are the summary statistics for these data. So helpfully they've given us all this. Draw a scatter diagram to illustrate these data. Right, I'm not going to draw the scatter diagram for you, but if we just look where those marks come from. So if you look, it doesn't have to be that accurate. They've just got 0, 500, 1,000, etc. So you get a mark for the values of A, a mark for the values of T, and a mark for the axes. Right, part 2, state which of the two variables A and T is the independent and which is dependent. So remember, the independent variable is the thing that's kind of not being affected. It's the thing that the pilot is changing, that he knows, and that's going to affect the dependent variable. So here you can see he's changing A, which is the altitude, and then he's seeing what T, the takeoff distance, is. So if we see what they want for those 3 marks, so A is independent, T is dependent. So since the values of A are not subject to random variation, so something like that, which we were saying, so A is something he's decided, but are determined by the runways which the pilot chooses, whereas the values of T are subject to random variation. So really that's the key phrase here, is which of them are subject to random variation. Right, and then 5 marks, calculate the equation of the regression line of T on A. Okay, so I think the only thing that's a bit tricky here is that we've got to remember which is X and which is Y. In general, Y is going to be your dependent variable, A is going to be your independent variable. So you can think of T as Y and A is like our X. So we're probably going to want to go to our formula book and look at the regression stuff. So this is what we're going to be using. So this is for Y on X, and ours was T on A. So we've got it the right way around. Right, so first thing we're going to want to do is find X bar and Y bar, which in our case is going to be T bar and A bar. So T bar is going to be the sum of T divided by N. So 5987 divided by 7, which is not a very nice number. So let's call it, well, these are 3 significant figures, so let's give ours just a 4 until we get our line. Let's go 5. Right, and then A bar is going to be similar. It's going to be the sum of A divided by 7, so 6,300 divided by 7, which is 900. It's a nicer number. Then we've got to work out B, which is essentially the gradient of our line, and that's going to be SXY, so in our case it's going to be SAT, over SXX. Now this is where you can make a mistake, so remember it's got to be the X one here, so ours is going to be SAA. Right, good. So we're going to have to use this form of the formula. So it's sum of xy over n minus xy. So in our case, it's going to be the sum of at over n minus, what did I just say? Minus a bar t bar. And that's all going to be over SAA, which is the sum of x squared over n minus x bar squared. So in our case, the sum of a squared over n minus a bar squared. So you should be able to put that all in your calculator as one calculation, I think. So at the top we've got 6,037,800. I'd write it out for the examiner just to show you know what you're doing. And that's been divided by n, which is 7. And then we've got to take away a bar, which was 900, times by t bar, and I'm going to put in the exact number, 5987 over 7, and that's all over the sum of a squared, which is 8,190,000 over n, which is 7, minus a bar squared, so minus 900 squared, and that gives me 0.2577. Okay, so we've got the gradient of our line, and we know it goes through A bar, T bar. So you can use like the equivalent of y minus y bar equals b x minus x bar. We just got to remember in our case it's going to be t minus t bar, so t minus 855.29 equals b, which is 0.2577, x minus x bar, so x minus 900. And they haven't asked us to give it in any special form, so I think we can leave it like that. Alright, so let's look at the mark scheme. So you get a mark for A bar and T bar. You get a mark for attempt gradient, so doing this. So we got 2.2577, they rounded it slightly shorter than that. And then they've subbed it into this and A1 FT for complete equation. Okay. So it looks like they do want it in that form, so we would have had to expand ours out and write it like that. Okay, so bear that in mind in future. Right, part 4, use the equation of regression line to calculate the estimates of the takeoff distances for altitudes 800 meters and 2,500 meters. I'm just going to borrow their line once they've times it all out. So their t equals 0.258a plus, was it 623? Yeah, right, so the takeoff distances for altitude is 800. I just want to make sure that altitude is the right bit. Yeah, altitude is A. So if we sub in 800, so I'm going to do 0.258 times 800 plus 623 is 828.6 meters. And then for the second one, I've just got to do the same thing but with 2,500. So I'm doing 0.258 times 2,500 plus 623, and I get 1,265.5 meters. And then comment on the reliability. So this is always going to be about, are you interpolating or extrapolating? So if we look, 800 meters is within our range of data. It's between 600 and 900, whereas 2,500 is outside our range of data. So that the one for 800 meters is going to be more reliable than the one where we're extrapolating, because we don't know what's going on past 1,800 meters. Right, calculate the value of the residual for the data point where A equals 1,200 and T equals 923. So what we're going to do here is sub in 1,200 and see what we get. So 0.258 times by 1,200 plus 623 is 932.6 meters. So basically this is what our equation predicts we would have got, but the actual value is this. So the residual will be, what we do is take the actual value and take away the observed value. So the actual value is 923, and then we take away 932.6, and we get minus 9.6 meters. So that what that minus shows is that this is below our line of best fit. Right. So you get a mark for each of these for that, and then a valid relevant comments relating to the predictions, such as first prediction is interpolation, second is extrapolation. So for this one, you get a mark for getting 933, which is basically what we got. A mark for minus 10. Did we get that? That sounds a bit off. They've rounded it to 3 significant figures. The residual is negative because the observed value is less than the predicted value, so that's what you need. So if it's positive, it will be the other way around, where the predicted value is higher than the observed value. Okay, question 2. On average, 2% of a particular model of laptop computer are faulty. Faults occur independently and randomly. Find the probability exactly one of a batch of 10 laptops is faulty. Right, the hard thing here is you need to recognise what kind of distribution this is. Now if you think about it, we've got a load of laptops, some work and some don't. So this will be a binomial thing because we're testing each one, and then it can either be true or false, basically, i.e. faulty or not faulty. Okay, so our x is going to be binomial with an n of 10, and p is, so the probability it's faulty is 0.02, and the probability exactly 1 will be faulty is going to be 10c1 times by 0.02 to the 1 times by 0.98 to the 9. So that gives you 0.1667. State the conditions under which use of a Poisson distribution is appropriate as an approximation to a binomial. Right, now here they're not looking for all the stuff about independent, random, uniform rate and all that, because if it's already a binomial distribution, that's already assumed, so we know the faults are independently and random. So for this to be true, the number of trials has to be large, so i.e. n has to be large, and the probability has to be small, so p is small. And I imagine that's all they're looking for. Right, so you get 3 marks for that, which is alright for a S1 question, and then n large, p small. Right, so now we see n is large. A school buys a batch of 150 of these laptops. Using a Poisson approximating distribution to find the probability that there are no faults in this batch. Okay, so if x is originally a binomial with 150 trials and p 0.02, then we know x is approximately a Poisson with lambda will be np. So in other words, 150 times 0.02, which is 3. That's a nice number. Right. So then they want the probability there are no faulty laptops in the batch. So in other words, the probability x equals 0. So if you remember, it's going to be e to the minus lambda times by lambda to the x over x factorial. So because this is 0 here, it's going to be e to the minus lambda, so minus 3, times by 3 to the power of 0 over 0 factorial. So it's just, as is the case when you're finding out the probability x0 for any Poisson distribution, it's just e to the minus lambda. So I can do e to the power of minus 3, we've got pi. E to the power of minus 3 is 0.0498. Right. There are more than the expected number of faulty laptops in the batch. Right, well we know the expected is 3, so we're looking for the probability x is greater than 3. So we're going to have to use our tables now. So we're going to have to do 1 minus the probability x is less than or equal to 3. Because this one isn't including 3, so this one is going to have to include 3. Right, so we've got to find our Poisson tables, which is easier said than done. So go through all of the binomials. Right. Oh, we've gone a bit too far. There we go. Here's lambda is 3, and we want the probability x is less than or equal to 2, so we're going to be using that 0.4232. So 1 minus, whoops, pick the wrong one. We actually want 6472. So I'll make that 1.6472, 0.3528. Okay, use a suitable approximating distribution to find the probability there are at most 50 laptops in this batch. At most, sorry, 50 faulty laptops. Okay. Oh, sorry, I've kind of jumped ahead a bit. Right, so now we've got a batch of 2,000 of these laptops. So what you'll notice now is if you do 2,000 times 0.02, you get 40, which is off our tables. So the highest lambda value we've got is 10.9, it looks like. So because we're at 40, we're going to use a different distribution, which hopefully you'll have worked out is a normal. So the exact distribution of the number of faulty laps in the batch. Now they're not asking for anything to do with the normal distribution. They're asking for what's the binomial. So the binomial is 2000, 0.02, and the approximating distribution, we're going to have to use normal. So remember, for that, mu is going to be 2000 times 0.02, which was 40, and sigma, so the variance, sigma squared, is going to be npq. So in other words, 2000 times 0.02 times 0.98, and you get 39.2. So remember, that means sigma is the square root of 39.2. So we can say x is approximately distributed as a normal with 40, 39.2. Right, state the exact, we've done that. Using a suitable approximate distribution, find the probability there are at most 50 laptops in this batch. Right, so we want the probability x is at most 50, so x is less than or equal to 50. Now remember, whenever you're equating to the normal, or if you're ever going from a discrete distribution to a continuous distribution, you've got to worry about a continuity correction. So what that means is, because the normal is all continuous and this is discrete, we've got to imagine like what would round to 50 basically. So because we want to include 50, that means we want the probability that x is less than 50.5. Because we want to include the kind of, if you imagine the bar chart of our discrete to our continuous, it goes like 49, 50, 51. Because we want to include the bar with 50 and anything below, the bar itself is going to go up to between 50 and 51, so 50.5. And then you can go about doing your your normal calculation. So this will be the probability z is less than 50.5 minus mu over sigma. So remember, that's square root of 39.2. So that is 1.677. 6771. So that should be the probability that z is less than. Right, so because it's less than, if we imagine a drawing of it, not a great drawing. So we're looking for this area, and that is what the table tells us. So the table will tell us the area below. So let's look for 1.6771. Right, so correlation, here we go. So we've got 1.67. So that's going to be 0.9525 with another 7 on the end. So we've got to add 7 to that, so that'll be 9532. But that's only 1.677. So because it's a 1 as well, we need to go 1/10 of the way along to the next one, which, because it's just 7 and 8, isn't actually going to make a difference because it's only 1 along, so 1/10 of 1 is still closer to 0. Right, so our answer will be 0.9532. Okay, so we get a mark for 3 there, a mark for this first answer. Expected number is 3, you get a mark for saying that, and then a mark for getting to 0.3528. A mark here for binomial, and a mark for these. A mark for using normal, and then a mark for mu and sigma squared. A mark for doing continuity correction. A mark for probability using the correct tail, i.e. you're not doing 1 minus or anything, and then 0.532. Okay. Question 3. In an English language test for 12-year-old children, the raw scores X are normally distributed with mean 45.3 and standard deviation 11.5. Find the probability X is less than 50. Okay, so if X is less than 50, that means Z is going to be less than. Now the reason I'm not doing a continuity correction here, even though it's a score, is because it says the scores are normally distributed. It doesn't say they have to be whole numbers. so we don't have to worry about that here. So here we're doing 50 minus 45.3 over 11.5, which is 0.4087. Now once again, if we imagine our crudely drawn normal distribution, that's here and we want the probability it's below, so we are just going to have to find phi, i.e. the number from the tables of 0.4087. Right, so there's 40, 8 would be 29, so 6554 plus 29 is 6583. But we've also got to go 7/10 of the way along the next number, because that's just 0.408 and we want 407. Sorry, 4087. So you can see the difference between the 29 and the 32 is 3. So if we find 7/10 of 3, which is 2.1, that means we've got to go along. So the nearest integer to 2.1 is 2, so we'd go along another 2, which would mean this will be 0.6585. I'm just going to double check that, because it usually depends which way the wind is blowing over how they like to allocate those marks. Right, so they do have 85. So you have to use the use of difference table. So in other words, using those differences in the table. When the candidate's answers suggest that he/she appears to have neglected to use the difference column in the normal distribution tables, penalise the first occurrence only. So you're not going to get penalised again. Right. In other words, you might get part B wrong because of that, and you're not going to get punished twice for the same mistake. Right, so now it wants the probability that the score is between 45.3 and 50. So what you hopefully spot there is that 45.3 is the mean. So, and then 50 is here, and they want this area. Now we've already worked out the whole area, including this left-hand part. So we just need to know, well, what's the area of this? So because it's the mean, this has to be 0.5. In other words, there's a half chance we're below the mean. So all we've got to do is do 0.6585, take away 0.5, and we get 0.1585. Right, good. Part 2, find the least raw score which would be attained by the highest scoring 10% of children. So what they mean is, this area is 10%, what is this score going to be? So if we think, well, that means the area below is 0.9, so we always need to know the area below, because that's what the table is focused on. So if we go to our tables, so here's the inverse table, and if we go down to 0.9, if you notice they've only got it from 0.5 and up. So if we go down to 0.9, it tells us the z value must be 1.282. So in other words, x minus mu over sigma has to equal 1.282. So if we sub in our numbers, so x minus 45.3 over 11.5 is 1.282. So 1.282 times 11.5, add 45.3 is 60.043. So let's say it's 60 to 3 significant figures. Okay, and they're happy with that. So 1 mark for 1.282 seen, 1 mark for your equation in k, we just use x, that's fine, and 1 mark for 60. Okay. Part 3, the raw score is then scaled, so the scaled score is normally distributed with mean 100 and standard deviation 115. The scaled score, so this is where the continuity correction comes in, is then rounded to the nearest integer. Find the probability that a randomly selected student gets a rounded score of exactly 111. So if it's rounded to 111, that means the score must be between 110.5 and 111.5. So then if we standardize it, so do 110.5 minus 100, take away 15, sorry, divided by 15, that gives us 0.7, and 111.5 minus 100 divided by 15 is a horrible number, so 23/30ths, which is 0.7667. So it's really 0.76 recurring, but we'll just put its 4 significant figures. Right. So if we think about our normal distribution, so always draw a diagram. Here's 0.7, here's 0.7667, and we want this area. So we're going to have to do the area below 0.7667 and the area below 0.7. So the area below 0.7667 is going to be the thing we look up in the table for 0.7667, and then take away the thing we look up in the table from 0.7. Right, so the first one's going to be more difficult. So 0.7, where are we? 0.766. So that's going to be 7664 plus 18. So now we're at 0.7. Sorry, I'm getting mad. Now we're at 0.7782, but we also need to go 7/10 of the way along this. So 7/10 of 3, that's come up again, is 2. So we're going to have to go along 2 from this. So I make that 0.7784. And then we need to take away 5 0.7, which is a lot easier because it's an exact number. And that's 0.758. Right, so 0.7784 minus 0. What did I just say? 758. I can't even write things down properly. Is 0.0204. Right, let's check that. It's not 100% confident. Yeah, so again, you won't get punished for getting this slightly off if you made the same mistake before. So you're only going to get punished. You're only going to lose 1 mark in a whole S1 test, basically. Right, where are we? Here we are. Right, in a mathematics test for 12-year-olds, the raw scores y normally distributed with mean mu and standard deviation sigma. Given the probability y is less than 15 is 0.3, probability y is less than 22 is 0.8, find the values of mu and sigma. Right, so let's draw a diagram. So we don't know mu or sigma, but we do know, oh my god, that's a bit better. So we know the probability y is less than 15 is 0.3. We know the probability y is less than 22 is 0.8. So the whole area below that is 0.8. So I'll just put that at 0.2 there to remember. So what we need to do is work out both the z values that correspond to these x values, because we know that 15 minus mu over sigma equals some x value, and 22 minus mu over sigma equals some x value, sorry, z value. So if we find both of those, then we can do simultaneous equations and solve them. So first of all, we know the area below 22 is 0.8. So we can look up in the table, well, where does 0. So inverse 5 0.8 is 0.8416. So we know the z value for that value 22 must be 0.8416. Right, now the one for this 0.3 is a bit trickier. Because the tables don't show negative z values, and because this is below the mean, it's going to be negative. So We do know this whole area is 0.7. So what we can look up in the tables is, well, what's the z value that has the area below it equaling 0.7, and then because ours is reflected, ours will be minus that. So 0.7 is 0.5244. So it's going to be minus 0.5244. Okay. Right, so now we have to solve these simultaneous equations. So the way I would always do this is make mu the subject. So if we make mu the subject of the first one, it's going to be 15 plus 0.5244 sigma equals mu. So what I've done basically is times by sigma and then moved it around a bit to get mu on its own and positive. And then for the other one, it's going to be 22 minus 0.8416 sigma will equal mu. And because they both equal mu, we can set them equal to each other. So we'll have 15 sigma equals sigma. So if I solve that, we do 22 minus 15 is 7. 0.5244 plus 0.8416 is 1.366 sigma. So sigma is 7 divided by 1.366, which, let's give it to 3 significant figures, is 5.12. I'm going to keep it in my calculator and sub it into this top equation. So 15 plus 0.5244 answer is 17.7, let's say, to 3 significant figures again, which sounds about right. Okay, so they've done all the 4 significant figures, but are still correct. Yeah. Okay, so you get a mark for this scene or this scene, a mark for at least one equation in Z, mu and sigma, so something like this, a mark for having them both correct, a mark for attempt to solve them, and then a mark for both of these. So I think in general 4 significant figures is right unless it's a probability, is a good rule of thumb, in which case you can do 5 significant figures. Right, question 4. A council provides waste paper recycling services for local businesses. Some businesses use the standard service recycling paper, others use a special service dealing with confidential documents, and others use both. Businesses are classified as small or large. A survey of random sample of 285 businesses gives the following data for size of businesses and recycling service. Write down the null and alternative hypotheses for a test to examine whether there is an association between the size of business and recycling service used. So for this, basically the null hypothesis is there is no association between size of business and recycling service, and then the alternative is always going to be there is some association between size of business and recycling. So whenever you're doing a what's it called, contingency table, it's always going to be about is there association or is there not association. Okay, so no association, some association. Part 2, the contributions to the test statistic for the usual chi-squared test are shown in the table below. So they've done all the work for us. They've even added them up for us. Calculate the expected frequency for large businesses using the special services. Verify the corresponding contribution. So if we go back to our table, large businesses using the special services. So we want to work out basically if these weren't associated at all, how many businesses would we expect to be using? How many large businesses would we expect to be using the special service? So to do this, to start, we need to work out all the marginal totals. So I'm going to do 35 plus 26 plus 44 is 105. And then 55 plus 52 plus 73 is 180. 44 plus 73 is 117. I mean, I guess we don't need to work out all of these. We only need the ones corresponding to special and large. But let's do it anyway. And there are 285 businesses in total. Right, so really now we can forget about all these values and we want to know, if we assume there's no association, how many businesses would we expect to be in this cell? Well, there's 78 businesses use a special service out of 285. So the probability to use the special service is this. The probability that also a large business is 180 out of 285. So that's the probability any one business will be in this cell. And then we times it by 285 because there's 285 businesses we're testing, basically. Now, a lot of people they'll kind of cancel out these 285s and just do 78 divided by 285 times 180. And it just saves you a bit of work on the calculator, especially if you were having to do all 6 of these. So I make that 49.26. Okay, so that's the expected number of businesses we'd have. And then they also want us to verify this 0.1520. So that comes from observed minus expected squared over expected. So our expected was our observed was 52, and our expected was that number, that 49.26 we got. So it's going to be, my memory's like a goldfish, 52 minus that 49.26 squared over 49.26, but I'm going to use the exact number in my calculator. So 52 minus answer squared over answer gives us 0.1520. Alright. Carry out the test at the 5% significant level, stating your conclusion clearly. Alright, so given that we've got this, most of the work is done for us. So we've done our null and alternative hypotheses. Now we need to think about how many degrees of freedom have we got, and look up from the tables what the significance level would be. So given this is a 2 by 3 grid, our degrees of freedom is going to be 1 times 2. So we've got 2 degrees of freedom, 5% significance level. So now we can go to the tables. So 2 degrees of freedom, 5% significance level is 5.991. Right. So 5.991 is clearly greater than 0.6041. So this is basically, for a table with 2 degrees of freedom, this is basically what you'd expect to get as a sum of contributions. Generally, that's the highest it would be 5% of the time. So given that ours is nowhere near that high, we can accept H0. So what our quite small sum of contribution means, actually, all the observed were quite close to the expected values. So we can accept H0, and then you need to write something like, therefore conclude that there is insufficient evidence to show there is any association between size of business and recycling service. So you get a mark for test statistic, so using that test statistic, a mark for referring to 2 degrees of freedom, a mark for the correct critical value, a mark for not significant, and a mark for summing it up. So there's no evidence to suggest any association between size of business and recycling service used. Okay. Right, finally, the council is also investigating the weight of rubbish in domestic dustbins. In 2008, the average weight of rubbish in bins was 32.8 kilograms. The council has now started a recycling initiative and wishes to determine whether there's been a reduction in the weight of rubbish in bins. A random sample of 50 domestic dustbins is selected, and it's found that mean weight of rubbish per bin is now 30.9 and standard deviation 3.4 kilograms. Carry out a test at 5% level to investigate whether the mean weight of rubbish has been reduced in comparison with 2008. State clearly your null and alternative hypotheses. Right, so there's a lot going on here, and it's 8 marks. So we're going to assume originally they were normally distributed, and the average rubbish in the bins was 32.8, and standard deviation was 3.4. So now that they've taken a sample, so if they sample 50 bins, we would expect the means of those samples to be the same, and the standard deviation would be sorry, the variance would be divided by the size of the sample, so 3.4 squared over 50. Now just remember that's sigma squared, it's not sigma, so sigma is going to be 3.4 over root 50, so just something to bear in mind. Right, so our null hypothesis is that mu equals 32.8, and our alternative hypothesis is mu is, what do they reckon? There's been a reduction, so less than 32.8, and we could say where mu is the population, so use the word population, they like that, is the population mean of rubbish weight or something like that. What do they say? Weight of rubbish is what they use in the question. Okay. So in the sample, the mean weight was 30.9. So we want to work out then the probability x bar is less than 30.9. So now when we do our z value, we'll be doing 30.9 minus mu, but we'll be dividing by 3.4 over root 50, which was our value for sigma. Okay, so 30.9 minus 32.8 divided by 3.4 divided by root 50 is, as probability z is less than minus 3.951. So our z value is over minus 3.951. Now there's two ways you can go about this. We could try and look at this probability from the normal tables. The other way is we can look up the z value for the significance level. So we know it's at a 5% level. So if we look up what's the z value, so we don't know which side of this it is, where such that that area is 5%, then we can decide based on whether it's bigger or lower than minus 3.951, whether it's significant. So our tables, we're only going to be able to look up 0.95, and then we can do minus that. Okay, so let's go back to our normals. So look at 0.95, that's 1.645. So our z value in comparison to that, so minus 1.645 is here. So in other words, this area below this is 5%, so this area below this must be less than 5%. So what you can say in your question is minus 1.645 is greater than minus 3.951, therefore the result is significant, or reject H0 and conclude. So the other way you could do it is by actually just finding this using the normal tables as opposed to the inverse normal tables, and then you conclude, well, rejected H0, therefore there is sufficient evidence to show the mean weight of rubbish has decreased. So you get a mark for using 32.8, a mark for both of these correct, a mark for definition of mu, so where mu denotes the population mean weight of rubbish in the bins, good. Test statistic was that minus 3.951, which we found. Then a critical value being minus 1.645, a mark for a sensible comparison leading to a conclusion, and a mark for conclusion of words in context. So you will get all those marks if you find the probability z is less than minus 3.951. Okay, as always, hope you find that useful, and let me know if you've got any other papers you'd like me to go through. Cheers.